So now we're going to be looking at the dimension of a sum of vector spaces, u plus v. So what happens in that case? Well, just for a little bit of warm-up material, remember back in grade 4 when they told you that if A and B are regions in R2, okay, well, so they probably didn't express it exactly like this, but if you have two shapes, right, shapes in the plane, shapes, whatever, then the area of the union is the area of one piece plus the area of the other piece. Oh, and now I'm going to run out of space. Dang it. Minus the area of the intersection that they have in common. And the idea there is that if you've got these two different plane regions, then there's going to be some part that gets there might be some part that gets double counted, and that's what the intersection is checking out. So that middle portion is green, but then when I do this one, the middle portion also gets colored purple, so it got counted for twice. So you have to avoid that double counting and subtract that extra bit because it got counted twice. Okay. And then you took Math 248 or some equivalent methods of proof type course, and they said, oh, you know what, it works in an abstract context as well, where the cardinality of a union is the cardinality of one part plus the cardinality of the other part minus the cardinality of what they have in common. And it's pretty much for exactly the same region, or the same reason, right? And then if you go to grad school, you'll revisit this one, and they'll say, oh, the first one that is, and they'll say, oh, if these are measurable sets, because it turns out that not all shapes actually satisfy this property. But don't worry about that in this class, because measurable and non-measurable sets, that's where things start to get scary. Okay, so forget about that. All right, so let's look at the theorem. So Theorem 243. Okay, so if V is finite dimensional, and we have two subspaces, U1 and U2. Then the dimension of U1 plus U2 is going to be the dimension of U1 plus the dimension of U2 minus the dimension of the intersection subspace. Okay, so this proof is lengthy, so we're going to divide it into two pieces. So first off, I'm going to give you the sort of the goal and direction that we're going to go in, and then in the next video clip, we'll finish the proof. So here's the idea. Suppose that you've got a basis of the intersection. So this is the smallest part, right? So, whoops. So suppose U1 through UM is a basis of the subspace which is common to both, right? Okay, so note in particular what I just said, that this intersection is a subspace of both U1 and U2. Okay, so since U1, U2 is a subspace of U1, this basis for the intersection extends to a basis of U1. So it would have the original u's, u1 through um, and then as we extend it up to become a basis for all of u1, let's call the rest of them v's. So we have v1 through vj of u1, right? So that's if we extend the basis of the intersection up to being a basis of u1. But we could have gone the other way. So if we extend from the intersection up toward u2, and then we'll call these ones w's, the things we throw on in this case. All right. So then the claim, so I'm claiming now that if I take all this junk together, so u1 through um, v1 up through vj, w1 up through wk, so I've got this long old list now. So this is a basis I'm claiming for the sum space, u1 plus u2. Okay, so now let's just suppose that that claim has been proved. If that claim has been proved, so if so, then what do we have? Then the dimension of u1 plus u2 is going to be, so how do you compute the dimension of a space? Well, you count its basis. So how many things are in there? Well, we've got m u's and then j v's and then k w's, right? And I can rewrite this as m plus j plus m plus k minus m, right? Because all I've done is add and subtract these m's, which would cancel out, right? But I write it like that because then m plus j is the dimension of u1, and m plus k is the dimension of u2, and then m is the dimension of the intersection. And then reading from beginning to end, we have the identity that we're looking for, right? So all we have to do now is go ahead and prove this. And so that's what we'll do in the next clip.